we thought we understood the scale of the universe. For nearly 2 decades, a single image shaped our cosmic perspective. In 2004, astronomers pointed the Hubble Space Telescope toward what appeared to be an empty patch of sky in the constellation Fornax and let it stare for over 11 days straight. The result, known as the Hubble Ultra Deep Field, became an icon of modern astronomy and fundamentally changed how we viewed our place in the cosmos. What had looked like absolute darkness, a blank void containing nothing, was revealed to hold nearly 10,000 galaxies. Each one was a sprawling island of billions of stars, some with light that had traveled for over 13 billion years to reach us. This single image, capturing an area no bigger than a tiny speck against the vast night sky, became the foundation for a stunning estimate the observable universe contained as many as 2 trillion galaxies. For years, the ultra-deep field was the deepest map we had of the distant cosmos, our best window into the universe's childhood. Every single point of light in that image was not an individual star, but an entire galaxy, each containing billions of its own suns. Yet for all its revolutionary impact, Hubble's vision had fundamental limitations. Its 2.4-meter mirror captured primarily visible and ultraviolet light, the same wavelengths our own eyes can see. But the most ancient galaxies, their light stretched thin by the relentless expansion of space itself, had faded into the infrared spectrum, wavelengths that lay completely beyond Hubble's reach. And between us and those distant cosmic beacons lay vast clouds of dust, obscuring entire populations of galaxies from view. The ultra-deep field, for all its breathtaking detail and profound implications, was just a sliver of reality, fundamentally shaped by the technological limits of its era and the narrow slice of the electromagnetic spectrum it could observe. The universe, it turned out, was hiding far more than we had ever realized, patiently waiting for a new kind of telescope to reveal what lay concealed beneath the cosmic dust and beyond the range of visible light. The James Webb Space Telescope is not simply a bigger version of Hubble. It represents a fundamentally different kind of observatory built on entirely new principles. Its primary mirror stretches an impressive 6.5 meters across, absolutely dwarfing Hubble's 2.4-meter dish and capable of collecting more than 6 times as much light. But the real breakthrough isn't just in size. It's in what Webb can actually see. Webb is precisely tuned to observe in the infrared spectrum, wavelengths that allow it to pierce straight through cosmic dust clouds and capture the faint, stretched light from the earliest galaxies in existence, light that remains completely invisible to Hubble's instruments. Where Hubble's vision was like peering through a narrow keyhole into a vast room, Webb's capabilities are more like stepping back to take in an entire massive mural in one sweeping view. To truly appreciate the magnitude of this leap forward, imagine the Hubble Ultra Deep Field as a photograph printed on a single sheet of paper. At the same level of depth and detail, the equivalent Webb survey would fill an enormous mural 13 feet tall and 13 feet wide. That's the scale of difference we're talking about. The Cosmos Webb program was designed to harness Webb's revolutionary power for an unprecedented cosmic survey. Over the course of 250 hours of carefully planned observing time, the telescope meticulously scanned a patch of sky covering an area roughly 3 times the size of the full moon as we see it from Earth. Thousands upon thousands of individual exposures were painstakingly stitched together into one seamless mosaic, creating the largest and deepest panoramic map of the universe ever assembled by human technology. Within this single extraordinary field of view, astronomers have cataloged nearly 80,000 galaxies. Each one represents an entire city of stars, with some of these galaxies shining from an era less than 400 million years after the Big Bang itself. This isn't merely a bigger picture or a higher resolution version of what we already knew. It's an entirely new kind of cosmic atlas. The map reaches deep enough to reveal the universe's faintest and oldest structures, while simultaneously spanning wide enough to capture the grand architecture of cosmic evolution. The massive filaments of galaxies, the dense clusters where thousands gather, and the vast empty voids between them. For the first time in history, astronomers can study not just isolated individual galaxies picked out one at a time, but the full sweeping panorama of cosmic structure across billions of years of cosmic history, all contained within a single continuous frame of reference. Within the vast Cosmos Webb mosaic, the relatively nearby universe comes into sharp focus as a realm of mature galaxies, tangled mergers frozen in cosmic time, and colossal superstructures stretching across millions of light years. Here, astronomers have discovered galaxies in their prime grand spirals with graceful arms, smooth elliptical galaxies, and irregular shapes caught in the midst of violent collisions. The unprecedented scale of this map allows researchers to trace how these individual galaxies gather together into titanic filaments and massive clusters, forming the backbone of what astronomers call the cosmic web. Yet among all these familiar shapes and structures, one discovery stands completely apart from the rest. A system known as the Infinity Galaxy represents one of the most extraordinary findings in the entire survey. This remarkable object, cataloged at a redshift of 1.43, reveals a distinctive figure 8 silhouette in space. What we're witnessing is two disk galaxies colliding almost perfectly head-on with each other. Each galaxy remains clearly visible as a compact red core, circled by luminous rings of stars and glowing gas, their orbits dramatically twisted by the immense gravitational forces of their violent encounter. The collision is estimated to have taken place approximately 50 million years ago, and it's not just a spectacular display of cosmic violence. It has created physical conditions never before captured with such clarity. Between the two galactic centers lies a vast cloud of ionized hydrogen, glowing intensely with energy from a hidden engine buried within. Deep observations from JWST combined with data from the Chandra X-ray Observatory have pinpointed the unmistakable signature of a supermassive black hole, but with a shocking twist, it's not located in either galactic nucleus. Instead, it's lodged in the space between the two galaxies, embedded directly in the gas cloud itself, with its velocity matching the surrounding material to within just 50 kilometers per second. This off-center black hole, weighing in at roughly 1 million times the mass of our Sun, is joined by two more supermassive black holes. Each of the original galaxies harbors its own active supermassive black hole, confirmed by their characteristic broad hydrogen emission lines in the spectrum. The configuration is truly striking: three massive, actively feeding black holes, yet only one sits outside a galactic core, nestled in the turbulent aftermath of the collision itself. The evidence strongly points to what astronomers call a direct collapse origin. This black hole didn't migrate there or get ejected from one of the galaxies. It formed right where it sits, condensing directly from the dense, shock gas funneled together by the merger. Its presence, caught in the act by JWST's sensitive infrared detectors, offers an incredibly rare glimpse of how supermassive black holes might seed themselves during the chaotic process of galaxy assembly. The Infinity Galaxy stands as powerful testament to the value of wide, deep panoramic surveys. Only by mapping such an extensive area with such depth could astronomers spot such a fleeting, complex event. Its distinctive figure 8 form with a black hole actively growing in the void between colliding galaxies hints that the universe's most massive engines may sometimes ignite not in the settled hearts of established galaxies, but in the violent, turbulent spaces where cosmic worlds collide. Traveling deeper into the cosmos web mosaic takes us back to an era astronomers have dubbed cosmic noon, a period roughly 10 billion years ago when the universe was at its absolute peak in forging new stars. The galaxies discovered here are not just energetic and active. They display an unexpected level of organization and maturity that fundamentally defies our theoretical expectations. Webb's infrared vision is revealing a startling contradiction that challenges everything we thought we knew about galactic evolution. Galaxies that have already completely stopped forming stars, systems astronomers call quenched galaxies, appear in surprising abundance during an era when theory predicted they should all be blazing brilliantly with stellar birth. These dormant giants, some with masses that rival today's largest elliptical galaxies, sit quietly and peacefully amid a cosmic landscape that our models insisted should be dominated by youthful, chaotic star-forming systems. But the surprises don't end there. Webb has uncovered spiral galaxies displaying well-defined spiral arms, their disks stable and beautifully symmetrical even at redshifts between 2 and 3. In cosmic terms, this corresponds to just a few billion years after the Big Bang. Conventional models had strongly suggested it would take far longer for the universe to construct such highly ordered structures. Yet here they are, spiral arms winding gracefully around dense galactic cores, and some galaxies already displaying prominent central bars, clear signs of a settled, mature disk structure. The data demonstrate conclusively that stable disks capable of supporting these elaborate features were far more common at early times than anyone had anticipated. This early emergence of cosmic order is not merely a matter of visual elegance or aesthetic surprise. The presence of stable spiral disks and massive quenched galaxies at cosmic noon means that the physical processes responsible for shutting down star formation and sculpting galactic structure must have operated with remarkable speed and efficiency. The timeline for building complexity in the universe is shrinking dramatically with each new observation. At the very edge of what Webb can detect, pushing against the observational limits of even this revolutionary telescope. The record for the farthest confirmed galaxy now belongs to JADIS GS Z420. Its light began its long journey toward us just 290 million years after the Big Bang. Following close behind, MOM Z14 sets another new benchmark at 280 million years post-Big Bang. Both galaxies have been spectroscopically confirmed, meaning their distances are locked in with certainty by sharp Lyman breaks detected in Webb's NA-R-SPEC data. But the surprises extend even deeper than mere distance records. The ALMA radio telescope array has detected oxygen emission in JADIS GS420, revealing that heavy elements forged only inside stars, were already present at this incredibly early moment in cosmic history. This provides direct evidence that at least one complete generation of stars had already been born, lived out their lives, and died, enriching the cosmos with their processed elements. These ancient galaxies shine with the combined brightness of hundreds of millions of suns, all compacted into tiny, intense regions of furious starburst activity. Their very existence, combined with their detailed chemical fingerprints, suggests that galaxy assembly and stellar evolution began at a pace that completely defies the standard cosmic timeline we had constructed. Within the first 300 million years of cosmic history, the universe was already frantically busy forging complexity at a rate no one had predicted. The flood of discoveries pouring in from Webb's new map is forcing astronomers to fundamentally rethink the entire story of how the universe built itself from primordial simplicity to the rich complexity we observe today. Galaxies and supermassive black holes are now known to have formed earlier and grown faster than any of our models previously allowed. The standard cosmic timeline, once imagined as a slow, steady march from simplicity toward complexity, now appears more like a rapid-fire sequence of assembly and transformation. In just 250 hours of observing time, the James Webb Space Telescope's Cosmos Web survey has mapped nearly 80,000 galaxies, almost 80 times more than Hubble's iconic ultra-deep field revealed back in 2004. This sweeping infrared panorama exposes structures and individual galaxies stretching back 13.5 billion years through cosmic history, including record-breaking objects like JADIS GS420 and MAMA C420, both observed as they appeared less than 300 million years after the Big Bang itself. The data show conclusively that mature spiral galaxies, massive galactic mergers, and heavy chemical elements all appeared far earlier than any existing models had predicted possible. The pace of cosmic ionization, the rapid growth of massive dark matter halos, and the early seeding of supermassive black holes all demand entirely new theoretical explanations. Yet this comprehensive map covers just a small patch of sky, a tiny fraction of the full celestial sphere, reminding us that our universe is even larger, more complex, and more mysterious than we once dared to imagine, and so much more remains waiting to be discovered.